albino for gene T and normal for gene D. So what is the chance for that? Affected for gene T, normal for gene D, 1. So it would be 1/2. Or normal for gene T, affected with gene D, 0. Or very barely, but you have to consider that. Affected with both, 1/2 times this, again, 0. So these are all of the possibilities. So the chance would be 1/2 plus 0 plus 0, or rule. So the chance would be 50%. This, or this, or this. Question?
Yeah.
Yes?
So I understand like how it's like rare and stuff and all of that, so you would assume homozygous dominant. But in this like particular question, it didn't state whether or not it was rare. And so like the way I did it, I assumed that you'd have to take into consideration both whether or not it would be homozygous dominant or whether he was heterozygous. So then that would end up changing.
I don't know. I always, say to my students what to do. But in this situation, I don't know, by convention between you and your professor, what is the convention between you?
Well, we haven't done a problem like, well, yeah, we did do one last week, but like there was no like scenario where he was like, okay, in this case you have to assume homozygous dominant or something like that.
Albinism overall is not very prevalent.
Sure.
Yeah. And especially when a disease displays genetic heterogeneity. You have to, for one of these individual genes, you have to consider a person who is normal for an autosomal recessive homozygous dominant. This is, you're right. So you can just email Noor and let him know that what you consider.
Okay.
Yeah. Yes.
Can you just go over like the last 1/2 times 0, like where you got them?
Sure. Has he talked about probability rules? Okay, so whenever we want to know the chance of someone being affected with something, and we have some possibilities, the chance that this baby would be albino for gene T, or for gene D, or for both, you have to use a probability rule, which is called sum rule, and you add up the possibility of individual events. So the chance to be normal for, affected for gene T based on the Punnett square, which is 1/2, and normal for gene D, 100%. So in this scenario, the chance of this child to be albino for gene T, 1/2. Or another possibility, this child could be affected with gene D for albinism and normal for gene T. Chance for gene T to be normal, 1/2. And then affected with gene D based on the fact that all of the children have at least one copy of the D allele is 0. So it would be 0. No chance for this child to be affected with the D type of gene. Albinism, or being affected with both of them. Whenever we want to calculate the chance of someone being affected with both of the diseases, or we want to calculate the probability that 2 events occur simultaneously, you multiply them. So the chance to be albino for gene T, 1/2, and the gene D, 0, so it becomes 0. Then all of these are possible. So chance for being albino for gene T or gene D or both would be 1/2 plus 0 plus 0 would be 1/2.
I kind of have a question. I need to talk a second about it though. So I'm just going to use the gene and I'm going to say big A, little a, and this is regarding the parents when the question says the parents are normal. So if it's a dominant disease and it's saying that a parent is normal, their genotype would be little a, little a.
If it says, it depends on the wording. You remember in here, for example, suppose it says Mary and Jeff are normal.
Yeah.
But since the mother of Mary is affected, so you cannot assume
so all these
that.
can change to because of
If it says that parents are normal, penetrance is 100%, you know, then you can assume that parents are homozygous recessive.
Okay, and then so the next thing would be if it's a recessive disease and let's say penetrance is 100, then a normal parent would be big A, little a.
We don't have incomplete penetrance for recessive traits. This is a rule.
Okay.
Always consider penetrance for dominant traits first of all,
Okay.
and the individual who doesn't show the symptoms because of incomplete penetrance must be heterozygous.
Okay.
So always a normal allele must be present in order for a disease not to show.
Okay.
So big D for polydactyly for deafness individuals, homozygous dominant, cannot, you know, not show it. So always disease penetrates in homozygous dominant individuals for dominant traits. For recessive traits, as I said, it depends on what you have been told. By convention, I was in another class and the professor had said, whenever I'm talking about a normal person and she or he has, you know, and the disease is autosomal recessive, consider her or her as a carrier. But to me, it depends on the prevalence. So when we are talking about a rare disease, for autosomal recessive, whoever is normal is homozygous dominant, normal. Unless consanguinity is involved. So there are chances that these two guys have gotten the same abnormal allele from a common ancestor.
So I guess what I'm asking is for our exam Monday, when Nora asked that question, does he go by your line of thinking or does he go by the other line of thinking?
His own.
So
this is what I do. So, you know, based on the fact that, you know, there are lots of commonalities in science,
yeah.
Maybe we have different strategies of teaching, but science is science. So whenever diseases or alleles, frequency of alleles is low, like albinism, then you have to consider a person who is normal as homozygous dominant.
Okay, so the right answer he wrote in the key would be the
yes,
would be
the mother.
Big T. Big
yes,
T,
big T, little t, little t, big T.
Okay.
Got it?
I think so.
Okay. Now this one. So we did this. Okay. In these questions, which I'm sure is the trouble spot for some of you at least. Is it?
Yeah.
Okay. Okay, so in this, unfortunately, I cannot draw the pedigree on the board to write it on it, but I can show it with my cursor. So please try to follow my cursor to see what I'm looking for and what I'm doing, why I'm doing something. You see, this is a pedigree and in which autosomal recessive something, an autosomal recessive trait is shown. No wonder, because the criteria, very, very similar, is actually for autosomal recessive traits. And the question is asking, what is the chance that this 5 of 4, 1, 2, 3, 4, 5 generation, 5 number 4, this individual is going to be affected with this disease. Whenever someone is affected with an autosomal recessive trait, must be what? Suppose the gene is A. So what would be the genotype of this person? Big A, little a. So this means that this individual must get one little a from mom, one little a from dad. So if the parents are normal based on what you see, and we don't have incomplete penetrance in recessive traits. So when parents are normal, and just in case of passing one little a, this individual is going to be affected. So we have actually calculated the chance that the parents of this person of interest are carriers, right? So we are looking for the chance that this guy is a carrier and this guy is a carrier, because we don't know. Then if they are carriers, each one has a 50% chance to pass it on to this baby, and the baby would be affected, right? So we are looking for the chance of these two being carriers. But for autosomal all recessive traits, the only way that can help us to come up with this answer is to get hint from the people who are already affected. So these individuals in the bottom generations, usually, if you had someone at the top, use that individual. But in here, when you don't have anyone in here to be affected, so you have to consider these individuals. So how do they help us? First of all, you know that who is affected, whoever is affected is little a definitely. And you know that whoever is affected with an autosomal recessive, definitely, if the parents are normal, the parents are carriers, right? So we know that these two are carriers, definitely. And we know that because of her, these two are carriers, definitely, certainly. In order to know the chance of these two being carriers, you have to find a person for both of these guys, this one and this one, who lives in one of the previous generations. This individual must have 3 characteristics, okay, for mom's side, dad's side. 1, this individual should be genotypically related. So there should be a chance that that individual passes on the abnormal allele to this mom and dad. So we call them mom and dad. So we are looking for the chance that this one is a carrier, the dad. And how can he be carrier? When he gets one little a from one of the people from the past. But could this person be the wife of, for example, his uncle, genetically unrelated? No. So this person who can pass this little a to this guy must be genetically related. Second, this person, genetically, sorry. Okay. Second, this person must himself or herself be 100% a carrier, genotypically related to this guy, and then 100% a carrier, or has the allele. We have to be sure. If someone is affected, okay, we are sure that he or she has it. But when all of the individuals of the previous generations are normal, so you have to find someone whom you are certain is a carrier, certain, by some hints. And third, if there were some individuals with these characteristics, the first 2, you have to find the closest one, the closest genetic relative to that. This way your number, your estimation would be closer to the reality. Make sense? So we are looking for this individual for that side, for mom's side. So let's begin with the individuals who are affected. So these 2 guys are carriers, certainly. So when he is, this one, follow my cursor, is a carrier, definitely he has gotten it from one of the individuals of the parents. Dad is part of this family, but mom is not shown, first of all, so she has to be considered normal genotypically. Secondly, mom is not part of this family. Dad is part of this family in which we have a bunch of affected individuals. For example, you see this individual who is the great grandmother of this one is aunt of this one. So this is the dad side for this man who is the source.
Okay, so since you said mom was normal and it's a rare disease, mom is big A.
Yes.
Okay.
Yes. So the source of little a for this carrier man is this guy. Definitely. No other source, no other possibility. So now you are getting close to a person who has all of these characteristics. Genetically related, certainly a carrier based on the hints, and the closest person. You see, this individual has gotten this allele from his mother, but this mother is not the closest person. Genotypically, this is the closest person to this man. So you have to ignore her and find just this one. So he is definitely the carrier of this allele. The chance that he has passed this little a to the father is 1/2, right?